Okay, so did you guys have any questions on the Google form? Most of them were pretty good. But again, the beauty of having a lot of our assignments as Google Forms gives you that instant feedback. Do you have questions? Like, if you see like why you got the answer wrong, that's fine. Usually if you realize what happened, then you're not going to make the same mistake, and it kind of helps to solidify your understanding. But if you get something wrong and you don't know why, that's when you need to be like, I need to get this figured out. So always on any assignment, if you're not sure why something's wrong, please come and see me. That's the point. Like, it's not just to be like, okay, you need a grade, so do this. It's to see what you know, and it's for me to see what you know. And if there's still some confusion, we need to clear that up, all right? Because this information is definitely not going away. So just keep that in mind. Don't forget that that's kind of a key part of what we're doing with these assignments. And again, the Google Forms are perfect because you get that right or wrong, you know right away. So it's not like days later you get something handed back to you. So take advantage of that, and always come and see me. Have me explain, or try to get something clarified. Okay, and you guys are pretty good about speaking up about things, but just remember that that's always encouraged and always a great option. Okay, so we are moving away from our evidence of plate tectonics, that part of this unit, and we're moving into plate boundaries, right? So these plates border other plates. So you can see, all of these plates just kind of like state lines. Borders of plates are kind of the same thing. There's going to be, this plate coming up against this plate. Some of you made the observation during some of our activities that a lot of times, like the continents for Pangea aligned really well. Some of them you said that they were slightly off, not perfect, but still a pretty realistic fit. And I've said it, but underneath the actual crust that we can see, which is the continents, the plates a lot of times are going to align even better than the continents align. So what we can see on the surface aligns pretty well, but even underneath, it's even a tighter, better, more perfect fit of those plates. Because remember, the plates are the crust and the uppermost portion of the mantle. So basically, it's that lithosphere. So just kind of keep that in mind, that the plates are not exact borders or edges of our continents, right? This is showing the plates, but now it's kind of keying or coding them by what type of plate boundary exists between two different plates. So convergent, this reminds me kind of like of a dinosaur spiky tail, these little triangles, so you can see that like right along here. Divergent boundaries, you see arrows pulling away from each other. And then transform, it kind of looks like they're sliding, like you see it over here. If you're looking, the Juan de Fuca plate, which I just like to say that one, you can see over here. And so those transform boundaries. So those are going to be our three types of boundaries. And being able to look at a map like this, see the key, and be able to identify, okay, what type of boundary is taking place there. And then the big part of this is identifying what type of events or features might be found there because of the type of boundary that's located there. And so that's going to be a big part of this unit, or this part of the unit. So plate boundaries are a border between two tectonic plates, or multiple tectonic plates. Just like state lines, you go into Kentucky, you might cross the Ohio River and it says, welcome to Kentucky. Obviously, there's not like a physical line that you're crossing, but it is just, that designated location. And that's kind of the same thing. Like, you have this boundary, this border, and in my mind, I always kind of picture it like a state line. I think I told you that I went to Ecuador with my biology and Spanish departments when I was in college. And one of the things we got to do was we went directly to the equator. And so obviously not all around the world there's a line, but there's like these big places that are kind of like people go and visit, kind of touristy, and they have like a big line. So it's like you stand on the line, you're like, I'm in the southern hemisphere, I'm in the northern hemisphere, I'm in the southern hemisphere. Like there's like, they actually have like a physical line, and it's kind of cool. It did make you feel kind of like, oh my gosh, like this is crazy. I'm directly in the center of the earth, like splitting the globe in half, basically. And it was kind of a neat feeling. Obviously, we don't have lines on everything, but that's kind of a special one. But yeah, we have these boundaries, these borders, and there's going to be three main types, and very specific land forms and events and features are found at each type. And those are things that you're going to have to be able to identify and kind of like, okay, these things go with the transform, these go with the convergent, these go with the divergent. And again, trying to memorize it is a little bit more difficult. If you can kind of think about the process, like what is actually happening as plates would come together, what might happen logically as plates pull apart, and then you don't have to memorize as much. It's more just kind of using your common sense and thinking it through, and not trying to like memorize and keep it all straight. And that's something that I've been trying, and this is a skill, like not just for science, but for every class, even in real life, like trying to find connections, logically thinking things through instead of trying to memorize. That's just a skill that's going to be helpful in all aspects of your life, not just you being successful in the classroom, right? So keep that in mind, and I'm going to give you ways that I think of these things, kind of like we did with glaciers, to try to help make it make sense instead of it just be something else you have to try to memorize. Right, so we have plates that can come together, we have plates that can divide apart, and we have plates that can travel side by side, right? And so these hand motions are one of those kind of visuals. Come together, divide apart, travel side by side. Right, so convergent boundaries collide. CO, CO, CO. Collide, come together, convergent. All right. Then we have divergent, DI, DI, divergent, divide. It's kind of friendly that the words kind of sound like what they actually do. And then transform boundaries, TR, TR, transform boundaries, travel side by side. And those are some key parts of trying to start the whole just understanding of what's going on with these movements. So travel side by side, pull apart. And we've already talked about divergent. Where did we already kind of talk about divergent already this year? Yeah. Yeah, where the seafloor is spreading. Good. And convergent, we're going to see them come together. Notice how this one is showing one of the plates going down, right? We'll also talk about when they hit and like they both come up, what might actually form there. So take a second. What type of things could happen at these types of boundaries? So think about if two plates, I don't remember how it's on your paper. Does it have it separated? Yeah. So what kind of things could happen when the plates travel side by side, do you think? Or when they come together? Or when they divide apart? Obviously C4 spreading for dividing apart. What else?
Earthquake?
Yes, probably going to be the cause of some earthquakes. Very good. What else, Sarah? Possibly mountains, right? If plates come together, right? And some of you made that connection. The question on the gizmo that asked about the Himalaya mountains, and it was describing some of the plate movement, and some of you said that, like, well, the plates are like coming together, so maybe like they have to like, have nowhere to go, and they have to just push up, which is exactly what happens. What else? Any other thoughts? Events, land features, or formations? There's going to be one that you're going to be mad at that you didn't say. What do you think? That's the one. Yeah, volcanoes. Right? Without magma, and without movement in that mantle layer, in that asthenosphere, like what explains where this magma comes from and why, right? And it's all because those plates end up moving. There's also something associated with all three of our plate boundaries, and there are these things called faults. Not like it's your fault, it's my fault, but when they're talking faults, we're talking they call them fault lines. It's an area that is gonna form in response to stress, all right? And we're not talking like stressed out because, you know, the earth wants more water, or because there's too many people walking on it and it's getting all stressed out. We're not talking about that kind of stress. We're talking about stress that builds up because the plates are moving. And as the plates are moving, that causes kind of pressure, it can cause tension, and so it can only take it so long. Even kind of like how a person can, like, you know, like somebody's bothering them, they keep taking it. At some point, a lot of times people just snap, right, and they blow. They're just like, knock it off. Like you have your little brother or sister, and you're just like, you lose it for a second, and you're like, oh shoot, I'm sorry. But like, you just can't take it anymore, right? That's human nature. Like that happens to all of us at some point. The earth is the same way. And as these plates are sliding past each other, or as they're coming together, or as they're trying to stretch and pull apart, they can only take that stress for so long before they snap. So if you think about like my popsicle stick, right? I can push it and push it and push it and push it, and I'm adding force, but it can only take it so long before it's gonna snap, right? I'm adding pretty good amount, right? And these are getting kind of brittle, but the more brittle they are, the quicker they're gonna break, right? And so it can take it until it can't take it anymore and it snaps. And that's exactly what the earth does. And there's three faults that form, one associated with each type, right? And so it's the movement of the tectonic plates that provides this stress, and then the rocks or that crust at the surface are gonna be the ones that snap or break in response to that stress. And we call that area of breakage that fault line. And so probably the most famous ones that you probably have heard is the San Andreas fault line in California. And so obviously, you know, if you've seen the movie San Andreas, it does the Hollywood version of showing this fault reacting to the stress and breaking and sliding at that fault line. Kind of that shift that you see like right there. And so we have our three main types, and each type is associated with a particular type of plate boundary. So we have the reverse, which is associated with the convergent. We have the normal fault, which is associated with the divergent, and then we have a strike slip, which to me it's like they strike and then they slip past each other at a transform boundary as those plates are sliding side by side. So you are going to need to know which type of fault goes with which type of boundary. All right, so let's start with our divergent boundaries. And so if forces are pulling or crust apart in opposite directions, eventually the crust will stretch or divide. One way I kind of think about this, anybody here like Laffy Taffy? I love Laffy Taffy, like the big ones, not the little ones are okay, but I like the big ones. If you think of like taking one side of each and kind of dividing it, pulling it apart, what happens as you start to pull it apart? What happens to the taffy? Jonna, is that a hand or no? No? Sarah? It starts to stretch, right? And it starts to get real thin, doesn't it? And eventually it just like separates, right? If it's kind of room temperature. Now if it's cold, it's not gonna stretch the same way. But in my mind, it kind of like the crust is gonna keep pulling. And in a way, it kind of reminds me, at least in my mind, you know, kind of, and we'll look at a few videos that'll kind of show this a little bit, this stretching and kind of getting thinner. But dividing, these forces are pulling apart, and they're called tension forces, as the plates are struggling to separate and pull apart away from each other. We call that a tension force. Okay, and the faults that form at these areas are called normal faults. Normal faults. And so you can see this right here. And it looks like they drop up or down. all right? And again, a fault is going to form in response to stress. It's a brittle response, like a separating response. And usually this is because the movement of the tectonic plates provides the stress, and then the rocks of our crust show the response. So it's kind of like the plates are responsible for the force. So just like my hands are responsible for the force, but we're going to see the result of that force, and I'm bending it pretty good if you look right now, right? It's going to bend, bend, bend until it can't take it anymore, right? And so the response we see in the crust. The force is caused by the plates. Okay. And so these are good pictures. This is showing the seafloor spreading. So if you have oceanic crust that's experiencing a divergent boundary, at that fault line, it's going to pull. This entire thing is the ridge, right? And so it's not just like a single spot, but this whole line. And as it separates, right, we have magma that's there to fill it in, and that magma is going to fill it in. It's going to cool off because the ocean is so cold, the ocean floor. And so you're going to kind of get this magma that cools very quickly and forms kind of that ridge or that underwater kind of mountain range. And remember, this is what forms from basically the tip of South America all the way up to, North America along the mid-Atlantic, or along the Atlantic Ocean, forming that specific type of ridge we call the mid-Atlantic ridge. Right, so there can be small ones, there can be big ones like that. This is showing the same process, right? Oceanic crust separating, but this does also happen at continental crust, and we'll take a look at some of those examples later next week. Notice on your paper, if you flip it over at the top of page 4, it has weird font. It's dark and it's meant to stand out, and it says formations, right? It will form these things called rift valleys, which form at continental crust, and that's where it reminds me of the Laffy Taffy. It'll show it getting like smaller and kind of sinking down before it actually totally splits and divides. Earthquakes can form at these locations, mid-ocean ridges, which we already are familiar with. They form normal faults, and then they also are responsible for seafloor spreading. So divergent boundaries at oceanic crust, divergent boundaries at continental crust, plus our specific mid-ocean ridges that form because of seafloor spreading. So all of these things you're going to need to know, and we will make another graphic organizer that goes with plate boundaries next week, and that way you'll have a way to kind of keep all these things organized and be able to have somewhere to look very quickly at what goes with what. All right, so these normal faults, you need a way of remembering what goes with what, and here's how I remember it. A normal fault is obviously a fault line where the crust of one side is actually going to drop down in response to the plates pulling apart. So if you're looking here, the plates are pulling apart, and this side is going to drop down. Here's the way I remember it. Think of playing tug of war, all right? If Audrina and I have a rope, and we're playing tug of war, right? We're both pulling as hard as we can. Audrina might think she's going to be funny. What will happen if she lets go of the rope? What will happen to me? I'm going to fall down, right? That is the normal response. If things are pulling apart, like Audrina and I are tugging, maybe I should have said Aiden. You'd probably be the ornery one to let me go, right? Aiden and I are playing tug of war, right? He's pulling as hard as he can, I'm pulling as hard as I can, and he knows I'm pulling away from him. As soon as he lets go, right, I'm gonna bite the dust, drop down. That's the normal response, and that's what's happening here. They're pulling apart, pulling apart, pulling apart, and as they're pulling apart, when they finally cut loose, one is naturally gonna just drop down. All right, and really that's all you need to know about the fault lines. We could spend a whole unit just on fault lines and the things that happen there. But in general, that's what you need to understand. And that's how I remember that the normal faults go with divergent. think of tug of war. Well, obviously tug of war, you're pulling apart, you're dividing, you're pulling away from each other. And so the normal response to that is that if one side lets go, the other side is going to fall. And that's what eventually happens. They're pulling apart like tug of war. When one side lets go, this side's going to drop down. So if this side lets go, this side drops down. Okay? That makes sense? That's how I remember it. Okay, I'm gonna be honest. Year to year, I don't think about fault lines until we get to today, like this part of our notes, right? I don't have to keep back, like looking at it and refreshing my memory, not just because I've taught it for so many years, but because I think, oh yeah, tug of war, divide, one side drops down. That's what normally happens, right? I can picture it in my mind, Aiden letting go of the rope and me dropping down. Okay, so, you know, the normal faults, the normal reaction would be for one side to drop down. All right, moving on to convergent boundaries. Okay, so we said that divergent dividing is dealing with tension forces, like a pulling force. Okay, compression forces are what cause or what the reaction is of plates coming together. So as plates converge or come together or collide, that's a compression force that's at work. And again, think of a spring, you're squishing together, right? You're pushing it, right? And that's what's happening. You can see, and you guys said, okay, probably one of the things that's going to be formed are mountains, and that's exactly right. They kind of fold and fault and push on each other. Right, so if this is one side of the plate and this is another plate and they are pushing together, right, you can see my towel wrinkling up, folding, twisting, and like layering on itself, kind of like that picture is trying to show. Right, so again, converging together, and it causes that land to do exactly what that towel is doing. And that's how mountain ranges form, all along a plate boundary line. That's happening, and so that's how the Himalaya mountains, our largest mountain range, was formed. Right, and so there's two types of plates that this can happen. This can happen with continental plates, dealing with continental crust. And so the collision and compression, those pushing forces cause the rocks to fold and fault, just like my towel here, and this can form mountains. And our biggest example are the Himalaya mountains. And then it's these compression forces that cause a reverse fault. Okay, so we had a normal fault for divergent. We have a reverse fault for convergent. And here's that weird font again. It's bold, it's weird, it's italicized. And they can form mountains, they're going to form trenches, and we'll talk about that in a minute, subduction zones, reverse faults, earthquakes, and volcanoes. And again, I'm going to walk through all of these and again, trying not to have you memorize, but just think about it logically. If you're picturing continental plates coming together, it's real easy to visualize that those mountain ranges can form from this folding and faulting, right? We'll get to trenches and subduction zones Monday, right? And volcanoes. So, oh no, maybe today, sorry. The other form the other place that these can take place is at oceanic plates, obviously dealing with oceanic crust. So, at divergent boundaries, at a seafloor spreading situation, the crust is moving outward, parallel to the ridge on both sides, right? Can you guys visualize that? Good. From there, the crust just keeps getting pushed and pushed and pushed. It's got to go somewhere, right? I think it was Zach, and he's not here today, so he's missing it, asked if it would hit the continental plate and just form big mountains, right? If they would be the same densities, that's exactly what would happen. But the oceanic crust, because it has all that force of the ocean, it's thinner and it is more dense than the continental plate that it is pushing up against. So this is continental crust, this is oceanic crust. Probably like somewhere over here, we have seafloor spreading happening. So the crust keeps getting pushed, until eventually that old crust that used to be at the center of the ridge is now at the edge of the continental crust. It's more dense. What do more dense things do? What are they gonna do, Fletcher? They're gonna sink, right? And so as they sink, that happens at something we call a subduction zone. It subducts beneath the less dense continental crust. And the ocean plate ducks underneath the continental plate. Sub meaning under, so it's saying it ducks under the continental crust. So it's going, and then whoop, goes straight down. Okay, and you can see it here. We have our thin oceanic crust, and it's being pushed because of seafloor spreading, and then whoop, it hits continental. It's going to subduct or duck under. Okay, and so if an oceanic plate converges with a continental plate, the denser oceanic plate slides under that less dense continental plate. All right, so if you think back to that seafloor spreading at mid-ocean ridges, and those are caused by divergent boundaries. Sorry, I made it too quick. Good. Divergent boundaries, magma's coming up, mid-ocean ridges forming, pushing the crust away in parallel, until you get to that continental crust. So where is the newest crust again? Is it going to be like here, or here? In the middle, right there. That's where that new magma's coming up, and it's going to cool, harden, become new ocean crust. Right at the center of the ridge. And this is what some of the questions from yesterday were asking you on that Google form. The oldest crust, where is that going to be? What do you think, Jackson?
Next to the continent.
At the very edge, right? The farthest away from the ridge. Good. And so if the new crust is continually being made, the old crust has to eventually go somewhere, or like Zach said, you're just going to have these huge mountains that would just continue to, like, at every coastline, you just have massive mountains. And that's not what we see. So something else has to be happening. And what's actually going on is that that ocean crust is going to subduct. So think about this. If you have new crust always being made, and it's being made by the magma in the asthenosphere, why doesn't the asthenosphere run out of magma? Because it doesn't. Why? Be like a 2-year-old. Why? What do you think, Sarah?
I think because the edges get pushed back down into the asthenosphere and become more.
Ooh, do you think that it's possible that that old oceanic crust, when it gets shoved back into the hot magma, could melt again and turn back into magma? Something has to happen, because we're not building giant mountains against the continental crust where the oceanic crust is hitting it, and we're not ever running out of magma. That's never happened in 4 billion years. So something has to kind of be recycling that old crust. And that's actually exactly what happens. Let's go ahead. Let's stop there. We have 3 songs. Let's just do one today, and then we'll start with the other 2 Monday.